Hi, welcome to this particular module, and in this module we will continue micromachining. So, in the last module what we have seen? We have seen bulk micromachining and surface micromachining. Now, let us see how can we use this micromachining techniques to fabricate sensor, and in this case we will take example of VOC sensor. VOC stands for volatile organic compounds. Now, what do you mean by volatile organic compounds? Compound that would be volatile, right. So, can you give me some examples? Yeah. So, petrol, then kerosene, acetone, methanol, ethanol, butanol, propanol, isopropyl alcohol, right. These are all volatile organic compounds. So, if I take a drop of this compound, if I put on my table, it will evaporate, it will be immediately it is volatile, it will evaporate, right. So, why we need to make a sensor? Of course, we are understanding micro machining, and that is why we have taken example of this particular sensor, but we should also know why we have to make a particular device. What is the role of this particular device? So, the role of fabricating or the application of fabricating these VOC sensors is in health, because this course is focused on clinical research, clinical perspective. We will talk about health. So, a person suffering from a lung cancer would emit a particular VOC in a higher concentration than other VOCs. So, what is our breath consists of? Breath consists of lot of volatile organic compounds, carbon dioxide, humidity, right. So, a healthy human would have a signature of VOCs below a certain level, but if you talk about a person suffering from lung cancer, that person will exhale higher concentration of NO2, or a person suffering from diabetes would exhale a higher concentration of acetone in breath. So, can we selectively detect this VOC, which is acetone or NO2 from rest of the VOCs? Yeah, of course, NO2 is a gas, but the sensors can be used for detecting gases as well. And if we can do that, if we can selectively detect that particular gas, whether it is acetone or it is NO2 from the breath, then we can qualitatively assess that a person is suffering from a particular disease. To quantify it, we should know how much concentration of that particular VOC or gas would be as the disease progresses. If you talk about diabetes, yeah, as the blood glucose concentration increases, is there any correlation between the acetone concentration increasing with blood glucose concentration increasing? If you have that correlation, then you can also quantify the data. So, not only you can detect that a person is having diabetes, but how much amount of diabetes, what is the blood glucose concentration, that can be correlated. So, the application of this particular sensor lies in this particular area when we talk about health. But if I talk about other applications, VOC sensors are used, or gas sensors are used in other applications as well. So, if you see the screen, what we are showing you today, and I always say we because any NPTEL course is not finished without teaching assistants, right. They are integral part of any course, and as a professor I have to give credit to my team of teaching assistants, and that is why I always say we are showing you another slide, right. Whether they have prepared this slide or not, I have prepared all the lecture notes, but they will be helping you out in your assignments and homeworks and other aspects during the course. So, coming back to this slide, you see here we will be talking about a VOC sensor fabricated using bulk micromachining, and this is the actual photograph of fabricated sensors using bulk micromachining, and in this wafer you can see array of sensors, many sensors fabricated on a single wafer as oxidized silicon substrate. So, if you see this particular figure, the on the oxidized silicon substrate is a blown up diagram. The first structure is a heater, first structure is heater. So, we have here heater, you can see SEM image of a heater. On the back side you can see this diaphragm, right, this etching that we have created. We have done this etching using bulk micromachining, this etching on the back side to create a diaphragm, we have used bulk micromachining. So, this etching on the back side you can see here in form of a pit. This heater is made using nickel. When we heat the heater, right, when we apply power, the heater will get heated up, and what is the maximum temperature that the heater can achieve, so that is why we keep on applying the power, and at a certain point you will see that the heater starts breaking. So, what is the temperature at which the what is the maximum temperature achieving capability of a heater, that is what we wanted to measure. Next part, if you see, next part is your interdigitated electrodes, next part is your interdigitated electrodes, or we call IDEs, right. So, over these IDEs we form a thin film of indium tin oxide, we form a thin film or we deposit a thin film of indium tin oxide. So, let us see how this process is done, how can we fabricate this sensor, let us see in the next slide, and then we will come on bulk plus surface micromachining. Okay. So, the starting wafer would be oxidized silicon substrate. Starting would be always silicon and then we grow oxide, that is why I said oxidized silicon substrate, right. So, we have oxidized silicon substrate, then we perform photolithography. So, for performing photolithography the next step should be spin coating photoresist. after spin coating photoresist, next step would be, now you guys should know, right, because we have studied photolithography. Next step should be mask, right. We load the mask, for creating the window. That means, we will create a window by etching silicon dioxide, because finally we want to create a diaphragm and then we are going to fabricate the remaining structure of the sensor, right. So, this is my mask. After having mask, loading mask, next step would be to expose wafer with UV light. Exposing wafer with UV light, right. What is the next step? Next step would be, of course, you see when I am telling about that we are spin coating positive photoresist, it should be assumed that after spin coating we will be going for soft bake, right. After positive photoresist we have to go for soft bake. So, I am assuming that you guys now know it, and that is why I am not writing it, okay. 90 degree centigrade 1 minute, we know it, right. And then after mask we have to develop the develop this wafer in a PR developer. So, when you develop the wafer in photoresist developer, you will get a structure like this. After that, next step would be hard bake. Again I am assuming that you guys know, but let us write it down for one time. Hard bake. After hard bake, you have to dip the wafer in BHF. Dip the wafer in BHF. When you dip the wafer in BHF, silicon dioxide will get etched, right. Silicon dioxide will get etched. Now, if you see, it should get etched on both the sides, right, on both the sides. Well, what I will do is, when you perform this PR developer, after PR developer and before hard bake, I will just spin coat photoresist on back side also, and then perform hard baking. Okay. I will spin coat photoresist on back side and then perform hard baking, and then we will go for BHF. This will protect my wafer, this will protect my oxide on the other side of the wafer, right. So, what I have? I have PR, I have SiO2, I have silicon, again I have SiO2, and I have positive photoresist on both sides of the wafer, right. Next would be, I will dip this wafer in acetone, dip this wafer in acetone. When I dip the wafer in acetone, what will happen? PR will get stripped, right. PR will be stripped off, sorry. Right, PR will be stripped off. Next step would be etching wafer in KOH 80 degree centigrade to obtain a diaphragm. sorry about this, let me draw it here. Right. Let us say this diaphragm is 100 micrometers, right. So, we now have a diaphragm, right, with 100 micrometers thickness, easy, until here is very easy, right. So, if I want to further work on this, then let me copy this. So, we are on the same page. Okay. So, now we have this structure, right, this structure. So, next would be, if I reverse that structure, what will I have? I will have oxidized wafer with a diaphragm, and this angle would be, we know it, 54.7 degree, right, angle would be 54.7 degree. Now, next step, after we have diaphragm, the first step on that front side would be heater, So, we can now deposit nickel. There is a nickel, SiO2, Si, SiO2. On nickel, I will spin coat my photoresist. How I am going to deposit nickel? By using E-beam evaporation, right. By using E-beam evaporation, we can deposit nickel, right, and this is my positive photoresist. Next step, we all know, I will just draw it on the same structure, right. Next step will be, after positive photoresist spin coating, soft bake 90 degree, 1 minute, hot plate. Then we should have heater, right, we should have heater. So, for having heater, we have to load the mask. For heater, after depositing nickel, we need to fabricate a heater. We have to pattern nickel to fabricate a heater. For fabrication of heater, we have deposited photoresist and then we have loaded a mask, right. After loading mask, next step we all know is UV exposure, right. After UV exposure, next step would be PR developer. So, for PR developer, when we develop a wafer with a photoresist, when we develop a photoresist, then photoresist will stay in this area. Why only this area? Because we are using positive photoresist and the area which is not exposed, right, will be stronger. So, we get this particular pattern. Next step, after positive photoresist, after developing the photoresist, next step would be hard baking. After hard baking, next step would be etching nickel. So, if I etch nickel, what will I have? If I etch nickel, right, the nickel will get etched wherever photoresist was not there, right. Wherever the photoresist was not protecting nickel, it will get etched. So, this is photoresist, this is nickel, then we have silicon dioxide, then we have silicon, then we have silicon dioxide. After nickel, next step would be acetone dip or stripping of photoresist. When we strip off the photoresist, what we will have? If I strip off the photoresist, I will have my micro heater ready. So, nickel, SiO2, silicon, SiO2, correct. I have my micro heater ready. Next step would be to form interdigitated electrodes. Now, nickel is heater, material for heater, right, but nickel is also metal, nickel is a metal. So, now if I want to fabricate an interdigitated electrodes on heater, I cannot do it, right, because it will be shorted, we cannot have metal and metal. So, what we can have? We can have a insulating layer between two metals. So, if you come back to the screen, the next step would be to grow silicon dioxide. So, let me draw silicon dioxide with a vertical lines like this. This is, we have actually grown silicon dioxide with help of PECVD. We will see in the chemical vapor deposition section, we will see why plasma enhanced chemical vapor deposition is used to grow silicon dioxide. So, silicon dioxide we are growing. Now, we have to perform photolithography, which you know, like positive photoresist, then we go for soft baking, then we go for developing of PR, after positive photoresist we go for soft baking, then we go for mask, UV exposure, PR development, and then we finally etch the required area, right. So, what we are doing here is that the unwanted area we etch, right. So, here what we will do is we do not want our silicon dioxide to cover the contact area, right. We do not want silicon dioxide to cover the contact area. For that, what we will do? So, let us draw here. So, these are contact, okay. These are heater contact here and here, these both are heater contacts. Okay. So, what we have right now? We have silicon dioxide which is grown by plasma enhanced chemical vapor deposition. This silicon dioxide is grown using wet etching, that is low pressure chemical vapor deposition. This one is done using PECVD, right, and we have nickel microheater, we have silicon, already we have written here. After this, next step would be spin coating of photoresist. Okay. Spin coating photoresist positive. Next step would be we do not want the silicon dioxide on the contact pads, right, otherwise we cannot apply power to the heater. So, we will have a mask, we will have a mask which is dark field mask. In this case we are using dark field mask, earlier all the cases we were using a bright field mask, right. Why? Because we want to protect silicon dioxide in all the areas on the microheater except contact pads, right. So, what is this mask? This mask is dark field mask. After loading dark field mask, next step would be expose, right, expose the wafer with UV light, expose the wafer with UV light. When you expose the wafer with UV light, and then develop the wafer, right, expose the wafer, then develop the wafer. So, PR developer, you develop the wafer, PR will develop like this, and we can see that we can access now silicon dioxide which is grown using PECVD, right. Correct. So, next step would be hard bake, and then we have to etch silicon dioxide. We have to etch silicon dioxide. So, we will dip the wafer in silicon dioxide etchant, and you guys know what is silicon dioxide etchant? Silicon dioxide etchant is buffer hydrofluoric acid, which is BHF, right, BHF. can very clearly see that silicon dioxide is etched from the contact pad of the heater, right. Silicon dioxide is etched from the contact pad of the heater. So, next step would be to dip this wafer in acetone, right. So, when you dip the wafer in acetone, what will happen? What will happen? The photoresist will be stripped off. Photoresist will be stripped off. So, let us remove the photoresist. Right. Photoresist will be stripped off. So, now what you have is silicon dioxide protecting your micro heater, right, except in the contact area. So, now if we apply power here or voltage here, right, because of the resistance of the heater, current will flow and the heater will heat up, But our idea is not to stop here. Our idea is to now fabricate interdigitated electrodes. You can see here interdigitated electrodes. So, how to fabricate interdigitated electrodes, right? How to fabricate this interdigitated electrodes. So, let us see how we can do it. So, I am just deleting this slide, so that we can work on the interdigitated electrodes on the micro heater. Now, we have insulator, right, we have insulator. So, we can now deposit a metal, right, that can be used for fabricating interdigitated electrodes. So, what is this metal? Let us use aluminum as a metal for fabricating interdigitated electrodes. I will just remove it. So, we can start from a wafer. So, I will draw here our wafer, and wafer has a micro heater. This is our oxidized silicon wafer with diaphragm, right. It has a micro heater and silicon dioxide protecting the micro heater, right. Okay. What is the next step? Next step is we have to create interdigitated electrodes on this structure. So, we will deposit a metal. Okay. So, let us have this pattern for our metal. Our metal is nothing but aluminum. This one would be our SiO2 from PECVD. This is our SiO2 from wet oxidation LPCVD, right, and this is our diaphragm 100 microns. Now, we want to create an interdigitated electrodes. So, what we want finally is a structure that should look like this. This is what we want from here, from this structure, right. So, next step would be, after this, next step is spin coating photoresist, right. So, quickly we will spin coat the positive photoresist. After positive photoresist, we have to perform soft bake. After soft bake, we will use a bright field mask and load it onto this wafer. Like this. Then we will expose our wafer with UV light, right, expose our wafer with UV light. After that, we perform PR developing. When we perform PR developing, we will have oxidized silicon wafer with a micro heater, silicon dioxide, aluminum, and photoresist. Right, positive photoresist. So, the area which was not exposed did not get became stronger, right, and did not get etched or did not get developed in the photoresist developer. Next step would be hard bake, followed by aluminum etching. So, when we performed aluminum etching, then what we will have? Performing aluminum etch. Right, this is what we will get. So, we have photoresist, we have aluminum, we have SiO2, we again have SiO2, we have silicon, and we have SiO2 at bottom, right, and then we have here our nickel micro heater, correct, because the photoresist will protect the aluminum, and thus the aluminum which was not protected, which you can see here, right, between the photoresist, will get etched. Now, after this, what is the next step? Next step would be acetone dip. So, when I dip my wafer in acetone, what will I have? I will have my interdigitated electrodes over insulator over micro heater over oxidized silicon substrate, and that is having a diaphragm. Still 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 we have not finished fabricating a VOC sensor. I enjoyed it a lot, because at a point it says that okay, it looks like this is the last slide. We have one more slide, okay. And without sensing layer you cannot sense, right, without sensing layer you cannot sense. So, and there is a role of micro heater, I will talk about it. Micro heater, insulator, interdigital electrode, last step, let us do it. So, come back to the slide, right. Let me just quickly rub it down. So, last step would be to deposit a sensing layer, and that our sensing layer would be indium tin oxide. It can be any other layer, it can be any metal oxide, it does not matter. It can be nanostructure of oxide or metal oxide nanostructures, it can be a thin film of a material, right. Whatever sensing layer you want to use, depending on your application of what gas you want to sense, you can use that particular sensing layer, right. So, several sensing layers such as like indium oxide, tin oxide, indium tin oxide, zinc oxide, tungsten oxide, right, are used for used as a sensing layer on the top of interdigital electrodes to form a sensor. So, let us write down, let us draw. This is the last step, right, this is the last step. So, we have SiO2, Si, SiO2, we have nickel, SiO2, then we have interdigital electrodes. Okay. Now, instead of performing a standard photolithography, I will show you something called lift off technique. What? Lifting off, lift off technique. Okay. This kind of techniques are used when you think that the etching layer, the etchant of the top layer will affect the bottom layer below it. What do I mean by that? Let us see here. Suppose I say that I have a wafer with aluminum, right, and I have SiO2 which I want to etch in a way that it should look like aluminum is here and SiO2 only stands here. Okay, you got it, right. If I have this wafer with SiO2 covered on aluminum interdigital electrodes and I want a wafer which should look like this, which is my aluminum, and SiO2 should only cover this two part of the design. So, I have to perform lithography, right, and finally, I had to dip this wafer in BHF, correct. So, why BHF? Because BHF is the etchant for silicon dioxide. So, if I want to, if I dip this wafer in BHF, what will happen, you guys know, the aluminum, this aluminum which is exposed will get etched in BHF. The BHF will etch aluminum as well. So, this technique cannot be used, right. this technique cannot be used, because my BHF is going to affect my aluminum, correct. Because you see, when I perform lithography, I will only protect this area with photoresist, right, because I only want to protect silicon dioxide in this region. So, this area will not get protected. When this area is not protected, that means that it will look like this. So, this is PR in silicon dioxide. If I put this wafer in BHF, this BHF will etch silicon dioxide here, here. When it reaches aluminum, it will also etch aluminum. Thus, this technique cannot be used. So, what is an alternative technique? What is an alternative technique? Alternative technique would be, if I want to have a wafer with aluminum and SiO2 only in this part, then how about this? I take the wafer with my aluminum interdigitated electrodes, right, and I coat the PR directly, photoresist, I coat the photoresist in such a way that my photoresist will cover only these two electrodes. It will cover, this is my photoresist. What I want? I want silicon dioxide, I want aluminum. So, let us have aluminum like this, it is easy to keep the pattern same, right. I have my silicon or oxidized silicon wafer, let us say, and my conventional way of performing photolithography, like the one we discussed just now, will affect my aluminum, because silicon etchant affects aluminum. In that case, what I am doing is photoresist, right, photoresist is patterned in this kind of way, and then on this photoresist I will deposit or I will grow silicon dioxide. I will deposit or I will grow silicon dioxide. Alright. Then what I will do? I will dip this wafer, this one, this wafer, okay, this wafer in acetone, What will happen? That the photoresist will get stripped off in acetone. So, photoresist, this much area and this much area will get stripped off, because photoresist will get stripped off. So, when this photoresist strips off, the silicon dioxide on photoresist will also get lift off, you get it. So, when this happens, when I dip this wafer in acetone, what will happen is that this photoresist, this area will get stripped off, this area will get stripped off. When this area strips off, this will take the silicon dioxide on top of it as well, this will take silicon dioxide on top of it as well, resulting in silicon dioxide that I want in this particular design. This is called lifting off, this is called lifting off the silicon dioxide, lifting off of the photoresist. Same lift off we will use in this particular example. So, let us see. Lift off technique we will use. Lift off technique is used when the final or the top layer etchant will affect the bottom layer pattern, right, top layer etchant will affect the bottom layer. So, now what I want? I want this material to get deposited on interdigitated electrodes, right. So, I will spin coat photoresist, then perform soft baking, then I will load a mask, that protects my photoresist in this particular fashion. Then I will perform UV exposure, right. Then PR developer. So, I will just draw it over here. I will get this kind of pattern, right. PR will get developed because it is a positive PR, right, and then I will deposit my sensing material on this. This is the top layer, like circle is my sensing material. After this I will dip this wafer in acetone. When I dip this wafer in acetone, what will I have? I will have my VOC sensor, ready to be utilized, So, when I deposit sensing layer on this kind of pattern, I will have finally when I put when I dip the wafer in acetone, I will have a sensing layer. I have interdigitated electrodes, right. I have silicon dioxide, I have silicon diaphragm, and I have my nickel micro heater. You see, this is your sensor, this is your complete sensor, and bulk micro machining is where I have etched my silicon. Now, the question that arises is why to do bulk micro machining? Why not to directly use oxidized silicon like this? Why to perform this bulk micro machining, right? So, you can see that there is a heater here, we are using nickel as a heater, right. Why we are using heater? Because if you heat the metal oxide materials, then at a higher temperature it will show a better sensitivity. At a higher temperature, the metal oxide semiconductor shows a higher sensitivity for different volatile organic compounds. Okay. So, there is a subject called thin film physics. If you understand that, then you will understand why and how the grains will create a depletion layer across it, and as you increase the temperature, based on reducing and oxidizing gases, the electrons will either be released, or it will be the conductivity would increase for reducing gases. For oxidizing gases, the conductivity would decrease and resistance would increase. So, this is a different subject. However, you just understand that for a gas sensor to work, we require it to heat at higher temperature if we are using metal oxide thin film materials such as zinc oxide, indium oxide, tin oxide, indium tin oxide, tungsten oxide, right. We require higher temperature for better sensitivity. So, for higher temperature we are integrating a micro heater, if you can see in the design, right. So, we have integrated a micro heater. Now, we need to have interdigital electrodes for the sensing layer, right. So, that we can measure what is the resistance of the sensing layer. That is why we have interdigitated electrodes on which we have the sensing layer. Now, since we have a micro heater, if we have to heat a wafer which is 500 microns in thickness, or you have to heat a wafer which is 100 micron in thickness, because we are creating a diaphragm, in which case the power consumption will be less. The power consumption will be less in, let us say this I say A and this I say B, then in case of B the power consumption will be less. Thus, bulk micromachining is useful to reduce the power consumption by the sensor. You guys got it? This is the application of bulk micromachining, and when you see this, you will be able to see a structure similar to the one that is shown in figure here. Here we have used indium tin oxide, right. Here we have used indium tin oxide. Now, in the next module, so in this module what we have learned? We have learned how to use bulk micromachining to create a sensor that can be used for sensing VOCs. In next class, let us see how can we perform bulk and surface micromachining to create structures or to create a sensor that can be again used for VOC, and then we will see what is the alternative technique. So, that you see, when you reduce the diaphragm, when you reduce the thickness of silicon, the power consumption goes down, but the mechanical strength of the material also goes down. So, how can we retain the mechanical strength and still reduce the temperature? Mechanical strength reducing, not temperature, reducing the power. Mechanical strength should be intact and the power should be less. How can we think about such kind of technology? So, in the next module we will see surface plus bulk micromachining, and we will also see this novel technique, plus we will also see how different actuators are fabricated, how the cantilevers are fabricated, what is a DRI structure, how wet versus dry etching can be compared, thin film deposition, we will see CVD techniques, 4 basic types such as ALD, PCVD, LPCVD and metal oxide, then we will also see MOCVD. So, this is what we will do. So, till then what I will say is just go through all the slides that we have discussed till now, and just understand how you can perform photolithography and how you can use bulk micromachining. In the next class, let us see how we can use surface micromachining. So, till then you guys take care, have fun, I will see you in next class.